So yesterday we started our first, I would say, excursion into paleoclimate reconstructions, and we'll try and continue it. And your questions were very good and appreciated. You had many questions, so feel free to stop me anytime if you have any further questions. Right. So the outline of the 1 hour that I will present today is as follows. In the first 1/3, I'll just go over, recap what we did last time, just to kind of refresh our memory, right? And then I'll go back to doing a northern hemispheric reconstruction, which is more robust, and I'll explain why. And then I'll move on to doing global reconstructions or spatial or regional reconstructions, which are not hemispheric reconstruction, but much more challenging. And that's what I intend to do towards the end of the lecture. Okay, so if you remember last time, we were trying to reconstruct temperature from proxy records, and these were tree rings, ice cores, speleothems, and so forth. And it was a high dimensional problem. We only had 150 years of data to calibrate proxies with instrumental records, and doing a regression was a problem. And I also put up what I call the poster child of paleoclimate reconstructions, the hockey stick and so forth. And what we were trying to do was, during the instrumental period, we had temperatures at different locations and proxies, not only in the instrumental period, but also going back. And what we were trying to do was to try and find the relationship between the proxies and the instrumental records, and then using the proxies in the, what I call the historical period, I try and infer what temperature could have been in the past. Right? And this was the general setup. This was the data matrix that we had. And this was missing. Temperature was missing, right, going back in time because of the availability of instrumental records. And we want to understand what was the climate 1,000 years ago or in 1200 AD. Right? And as I had put up last time, we had a network of proxy records, a network of instrumental records, and we were trying to find the relationship so that we can do hindcasts, right, and do uncertainty quantification of hindcasts. So the first 10-15 minutes is just a recap. So if you forget anything, just ask me. And I said there were a whole bunch of challenges that we had, including the fact that there isn't much data. How do we model processes evolving in time and in space, right? There's missing data all over the place. And what is the correct statistical or inferential approach to take? Now, if we had lots of data, then we won't have all these problems. The problem is that we have instrumental records only for the last 150 years, but we want to then try and understand what happened 1,000 years ago. So the period over which we can relate proxies, right, and how they are related to instrumental temperatures is limited. So we have to find more new age methods, right, as compared to standard regression, right? And as I had mentioned, the first part of the 3 series of lectures, I was going to focus on what I call northern hemispheric reconstructions. So I don't try and model, let's say, what climates of the past were in Mexico, or I say Mexico, right? I won't try and do that. It's considerably more difficult as compared to doing it in an aggregate way. Right? So I don't need to model spatial dependencies in that. Then at a later point, we will look at more regional reconstructions, which I think is, as you will see, is virtually very, very difficult and in some sense almost impossible to do. Because as we saw yesterday, that already doing a northern hemispheric reconstruction was not very satisfactory at times. So not always anyway. So doing it locally is even more challenging. And what I presented last time was methodology which was associated with the hockey stick and the so-called multi-layered uncertainty quantification, the first 2 parts. Today I will look at a robust reconstruction that we have recently proposed just now, in the last year and a half. That will conclude my northern hemispheric reconstruction approach. And then I'll move on to spatial or local reconstructions, right? So what I'm going to cover today is mainly robust reconstructions and the first part of spatial or local reconstructions. Okay, let's recap. What was the hockey stick? Well, what I was trying to do was, here was temperature and here was proxies, and I want to fit a linear model to the relationships, right? A standard least squares regression is what I was going to do, right? It was a high-dimensional system. There were more proxies relative to the number of years of data, right? Therefore, standard least squares methods were not applicable. So we used principal component regression to try and do the empirical orthogonal functions or coronal of expansions, right? To try and do the regression. So in some sense, you could think of this as a form of regularization, right? In applied mathematics, they use the word regularization for problems which are ill-posed. So in some sense, this is an ill-posed problem, and this is the way we get around it. And it's intimately related to Tychonoff regularization too, so, and we'll come to that. So the statisticians refer to it as principal component regressions, but please take that with a grain of salt, right? And then when we saw that when I made this point that actually the uncertainty around these hindcats are not very reliable because of various reasons, including first, there is temporal autocorrelation, number one, and there may be overfitting and so forth. And there was uncertainty in the hindcast because we are estimating parameters. So in order to really get at the uncertainty of hindcasting temperature way back in the past, we really need to model these processes very carefully, both probabilistically and statistically. And that's what we did with this GLS framework, where we had a generalized least squares framework. We had the same linear models as before, but the errors were auto-correlated or correlated in time. So temperature was moving in time. This allowed temperature to move in time from year to year in a correlated way. And that's more realistic. And in practice, they've seen that. So if you don't take that into account, problems will arise in terms of your variance estimates. So we did that, but we immediately hit a wall. And the wall is the following. Estimating the parameters is not available in closed form. So we have to estimate it using iterative methods. So we have a model, right? We have data. So of course you can estimate using maximum likelihood estimation or some kind of statistical techniques, but the answer is not available in closed form. And what I explained last time is that one could estimate the parameters of this model, this linear model with temporal correlation or autocorrelated errors using an iterative methods going back and forth. That one can show that it converges theoretically to a local optima. It's in fact a non-convex problem, so it's a local optima. So, and there are all kinds of other questions that we have to, in terms of this parameter space, the domain. So what you want to do is you have parameter space, right? So you have parameters beta, phi 1, phi 2, and sigma. You have a maximum likelihood surface. It's not a convex function of beta 1, beta, the regression parameters, or the autocorrelation parameters phi 1, phi 2. So one has to, and not only that, it's not only convex. Just because it's convex does not mean the answer is available in closed form either. Of course not, right? But it's not convex. It's multimodal, but also the answer, we have no answer in closed form. So we have to use an iterative method. And essentially, it's a partial maximization. You hold some of the parameters constant, you maximize over the others, over different sections, you go back and forth, right? And there is a rich literature on when that will converge and so forth, right? And also when we do overfitting during the calibration period, that underestimates the variance parameter sigma squared. That has to be adjusted. And also when we estimate beta, and we use these relationship between the proxy records and the instrumental temperature. Now we have a relationship. So I'm going to use those regression parameters to do hindcasting. Well, those are estimated, so they have uncertainty around them. That has to be taken into account. And we use the parametric bootstrap. If you're a statistician, you will know what a parametric bootstrap is, right? It's a way to do uncertainty quantification and take into account the fact that the beta coefficients are estimated, right? It was developed by Brad Efron. And this is a methodology to keep track of the various sources of uncertainty. Now, after all this methodology,
what is UQ?
Uncertainty quantification. Thank you for asking. UQ stands for uncertainty quantification.
It's become a buzzword.
Yeah, sometimes I use a nomenclature from the field, right? That's used in the statistics methodology and sometimes in the paleoclimate reconstruction field. But please stop me. UQ stands for uncertainty quantification. Right? And AR stands for autoregressive processes in time. right? After all that, I do a proper reconstruction, and then the uncertainty bands are much larger than we had initially thought. So this is the problem. Now, can we do better?
Well, another thing that, sort of bothered me when you showed this yesterday is that actually the increase from late in the 19th century to 1940 is as steep as the recent one.
Yeah. So that this increase here is as steep as here. That's what you're saying, yeah. So yeah, that's not during the reconstruction period. That's during the instrumental period, right? And this is not it's not really at the mercy of the reconstruction. If you were to do just a basic smoother here, the temperature increase here is as high as here, right? Of course, our interest is going back in time.
I understand it's not your fault.
Yes, of course, I take no responsibility to the warming. And I thought that was a foregone conclusion, but thank you for reminding me. I appreciate that. Yeah.
You shouldn't show that.
You mean this part here?
No, but you said it's a standard smoother. What is the smoother?
It's just the fit that we had. What we did was, when you do the calibration, during the calibration period, when this is fitted, that is a linear regression between temperature and proxies during the instrumental period. So I call it a smoother, a statistical method.
So the mean that you obtained was also different from...
Naturally, it would go through the points, right?
The mean was different from the hockey stick?
Oh, here, no, we don't have the hockey stick here. I have not superimposed it.
I'd like to compare whether the mean that you obtained, the uncertainties is
the uncertainties are here. The mean is the dark red.
The mean is similar
the mean is dark red. Oh, you mean compared to the hockey stick? The mean is similar here. Yes. The mean reconstruction is the uncertainty bands that go out. Yeah. Similar.
It would be good to show the previous...
the previous hockey stick. Yeah. When we take out the autocorrelated error, it's almost identical. It affects mainly the uncertainty. So that's why it's not imposed on this. Okay.
You see, the reason you don't see this on the hockey stick the way it was presented in AR3 is because there's this other thing that's superimposed on it.
Right.
Okay?
Which are
It's a visual, there are two lines on it. One is the blue line and the other one is a red line. And it becomes confusing exactly at that point.
So he's saying that if there's something superimposed on this, that could create a visual effect that could confuse the fact that the increase here is similar to the increase in the latter period from 1950 onwards. So that's a visual effect. It can be superimposed if you want. But if the same methodology without the temporal autocorrelation is the mean function, which is in red, the reconstruction of the mean is not very different.
I would hope.
Yes, it is the uncertainty that tells us, oh, well, how much of confidence can we put on the...
Another non-intuitive result is that the uncertainty is totally constant from when you have no data to when you have data.
Right.
That doesn't make sense.
Sense, right? Exactly. You would expect it to be, so that means that it's not very good. I mean, here, you're saying that the uncertainty here and the uncertainty here.
Are the same, yeah.
Right.
So that, I find more convincing the hockey stick because the uncertainty is reduced in recent times. How can you have the same uncertainty when you have many more instruments?
Right, so what happens with the uncertainty is that in this reconstruction, so I'll explain that there's a reason for it. In the hockey stick, they use fewer and fewer going back farther in time. Here I'm using 79 proxies, all of them which were available through the entire reconstruction period. So the same number of proxies are available throughout the entire period, including...
It's not increasing the number. You see, to be totally consistent, you have to use the same time series. you do not increase the number of times.
Exactly. So that's exactly what we're using.
But if we have observations, if we were going to do that in weather prediction, we would be using only railway zones.
So we addressed that in the RegEM approach at the latter part of this lecture. When the data decreases as we go back in time, the number of proxies decrease, we still want to make use of those proxies. Here, the goal is to illustrate a methodology about uncertainty. So certainly we do address it in a very comprehensive manner, and you'll see that. So, okay, so the problem that I had mentioned last time was that the little ice age is not reflected, right, around here. And as Michael also pointed out, uptick at the beginning of the period is not reflected. It's not dynamic out of sample, and I think you pointed it out. It's not very dynamic out of sample. And the uncertainty is very large, which is a problem. Okay, so how do we deal with this? Well, one way that we have thought about it is that, well, paleoclimate reconstruction is a very difficult problem, right? There are many irregular proxies, and part of the conversation yesterday was that we have different types of proxies, tree ring proxies. It's already a field of in its own right, and my understanding of it is pretty limited. And ice cores, right? And sediments, and lake sediments, and corals. So, as I say here, there are many irregular proxies with little understood relationships with temperature, right? So, a standard regression estimate, a standard regression or ordinary least squares, a very basic statistical method, is to model the conditional mean of the temperature. What a regression does is it says temperature given proxies is a linear function of the proxies. Proxies are given, right? Okay. So this is in fact, when you do a standard linear regression, if you want to regress y on x, what you're really saying is expected value of y given x is beta times x. You've seen that before. It models the conditional mean, right? Now the mean is not robust and can be very sensitive to outliers. Whereas we all know that the median of a distribution is relatively more stable. I use the word relative more carefully. So now many of you have seen the median, right, of a data set. Is much more. So given a data set, x1 up to xn, just scalar values, x1, x2, x3 up to xn, a bunch of values. If you were to take the mean, well, it's very easy to take the mean. It can be defined as the value a which minimizes the L2 norm of this function, right? Simple as that. So, and of course the median is related to, instead of the L2 norm, the L1 norm, right? So the absolute value. So this is one of the definitions of the mean and median, but you don't need these definitions. If you want to calculate the mean, you just sum them up and divide it by the total number. For the median, on the other hand, you order them and look at the middle value. So there are various ways of getting to it. This is just a mathematical definition that I put here, but I need that form for a reason. The squared term as compared to an absolute value term, right, has its advantages, right? It's easier, analytically tractable, right? This function, though it's continuous at the origin, right, it's not differentiable, so it's more difficult to work with, especially using Newtonian-Liouvillean calculus, right? Whereas this is more difficult to work with. So, so there are various reasons, and the mean is a very natural measure, of course. So we work with this. So our question is, well, instead of using least squares regression, the least squares regression, what it does is looks at the value of the regression coefficient where t minus beta p, the L2 norm, is minimized. That's what a regression really does. Y minus x beta squared. That's called the least squares regression solution. The value of beta which minimizes the L2 norm, the temperature, as a linear function of the proxies, the L2 norm of that, that's a vector, right? The L2 norm of that is minimized. Perhaps a better approach is to use least absolute deviations regression, which is to minimize the L1 norm of that difference, because it is more robust, because it resembles the median in terms of the relationship, right? So if you have a large number of values, especially tree ring proxies, which are not representative, or there is corrupted data, but mainly because the relationship between proxy and temperature is not well understood, we do not want extreme proxy values to really affect our temperature reconstruction. just like if you have a bunch of scalars, taking the median is less immune to outliers, right? And in the same spirit, we propose using a median approach, right? And a generalization of this least absolute deviation regression is something what we call quantile regression. Instead of modeling the median, the 50th percentile, you could model the 90th percentile of the temperature distribution, some extreme 10th percentile instead of the median. The median is a measure of central tendency, so you can do that too, right? At the same time, doing a least absolute deviation regression is more robust. However, the temporal autocorrelations that we have in time, right, is still there. So we have to develop a new methodology. First, getting this answer when the errors are, can be assumed to be independently and identically distributed, it's not available in closed form, the answers. You have to resort to linear programming, for instance, to solve this. It's not like the least squares regression where you take the design matrix, right, and manipulate X transpose X inverse, X transpose Y, and there you have it. You have the answer in straight form. You don't have to do anything iterative. Whereas here, it's not so clear. You'd have to use something iterative like linear programming, which is a staple, so it's not a problem. However, what's not available in the literature is if you have a model where you have autocorrelated errors, how do we get the parameters of this model? That's not available. So we've developed that methodology. So we've developed a new methodology for this kind of quantile regression with autocorrelated residuals. And the goal here is to combine robustness, right? A robust L1 type of penalty, right? L1 norm with temporal dependencies. Because in our paleoclimate applications, we cannot ignore temporal dependency. So that's what we are trying to do here. Okay? So let me go back and say, and summarize more mathematically what we're doing. We're trying to fit a linear model with temporal dependencies. Everything is exactly the same, where the residuals follow an autoregressive process of order Q. So you could go back to, epsilon t could be related to epsilon t minus 1 all the way to t minus 2 up to t minus q. This is an example of when there is just 2. The order is 2, right? Now, if I want to maximize this problem, right, in other words, estimate beta, phi 1, phi 2, and sigma, again, we are stuck in a non-convex problem. But not only is it non-convex, it's also not differentiable, right? Because there are points in which it is, it's continuous. Exactly, it's because of this.
Well, let me just ask you, I meant already to ask yesterday, but there were lots of other questions. Why not ARMA? Why do you restrict yourself to AR?
Yeah, we do try ARMA too, moving average models too, absolutely. We do. Mm-hmm. We have tried it, and what you can do is you can fit a moving average model, an autoregressive or an ARMA, and examine the autocorrelation functions and the partial autocorrelation functions and see which one is appropriate. And this is a better model. And I cannot take credit for it. It was first established by Lienitsch-Kahneman that an AR model was more appropriate. They established it first. Lienitsch-Kahneman, they established that an autoregressive process was the appropriate way to model the temporal dependencies. So the optimization problem for this is non-convex because I'm suddenly faced with this L1 norm. I call it an L1 norm, but just think of it as the absolute value. It has a non-differentiability problem at the origin, right? So this is non-convex. So that requires a way for us to develop an algorithm to try and estimate the parameter. It's also non-convex. So we need to show that the solution, really represents a local optima, right? And what we've designed is an iterative algorithm where at each step we ignore initially the autocorrelation error, get a value for beta, right? And then fit an autoregressive model to the errors from the model, and we go back and forth, like what we saw last time, where we had ordinary least squares regression, the standard L2 norm, plus temporal dependencies. It's more tricky here because of the non-differentiability part, right? So we have a method to fit this, and I won't put up the algorithm, right? And one can also demonstrate through techniques, from real analysis and optimization that it will converge. And we can also do uncertainty quantification of these parameters that we estimate using the bootstrap. Okay, now I'm going to implement this because I know you care about that more. I'm going to implement it and say, okay, I'm going to use the same data from man. There are lots of proxies, 1,000 proxies, more proxies than observations. I'm going to take 79 proxies, which go all the way up to 1000 AD, right? The kind of challenges that I have is the following. I have to choose an autoregressive order, right? What's the order of the autoregressive process? The innovations here, right? How do we model the innovations? Should they be normal? And again, I use principal components regressions because I have 150 years of data and 79 proxies, way too many predictors. Still, I need to get it down to a few, 10 or 5. So I use principal component regression. And then I undertake my robust regression, right? And we want to understand, well, when I do this robust regression, well, how many of these 79 proxies are significant at different values, significant values? So for the non-statistician in the audience, 10% means that if under the null hypothesis there was no relationship, getting these coefficient estimates has probability 10% or lower. It lies in the extreme tails of the distributions. And 0.1% means that it's only by random chance can you get these coefficients as this significantly related to proxies being significantly related to temperature. So the lower the alpha, the better, right? That means more significant. Okay. So we could, in fact, when we do this, remember yesterday I presented to you the standard model using the generalized least squares model developed by Lee, Nitschke, and Mann. When we use a robust, look, 48, a significantly higher number of proxies are now suddenly related to temperature, right? And in every significance value, it's higher than the competing methods. So certainly it yields, I mean, the original GLS approach yields many significant predictors, but the robust approach seems to do even better. So that means it's able to pick up the relationships better, and that's encouraging to see, right? So a question that you may want to ask at this point, how is the reconstruction? Well, here's the reconstruction that we do when we use the robust approach. Can you notice that the bandwidths have decreased? Well, I need to superimpose them. That's the first question she's going to ask, and I've done it already. I preempted it. Okay? So this was our original reconstruction that many of us were not happy with. Not happy with, and there's an emphatic no from here, right here. Not only from the audience, from right here. So, and I agree with you. So, and this was and when I superimpose them, look at the dark shade is enveloped inside the original one. Now, let me just go through what this is. The red is the reconstruction, the non-robust reconstruction. Black is the robust, and the black bands are the robust reconstructions, right? And the red ones are the non-robust reconstruction, which are on the. So one thing, what do we notice here? Well, immediately I notice two things. At the level of the means, the black curve, it's much more dynamic, right? So what's really what is really leading the action here are the proxies, not the autocorrelation, which is good because the proxies, the relationship between the proxies and the temperature, if it's modeled really well, you would see it out of sample, which is outside. When I'm hindcasting, it should be much more dynamic, and we're seeing that, right? And of course, another thing that you see is that what I complained about before, that the little ice age, well, we're starting to pick it up. And the uptick also with some.
I forget when the little ice age took place, between when.
It is about roughly right.
Yeah, it's roughly
it
this.
Sort of had the maximum dip around 1700.
Like around here.
I forgot the Danish army went over the ice to Sweden or the other way around.
I think it's to Sweden. Yeah, the Danish army went to Sweden, and they did not do.
No, this was totally cheap.
Yeah, it's much.
It's
much appreciated, though.
Yeah. And then there is sort of something like the medieval warm period, which lasted till about. Yeah, it was particularly warm during 1000 to 1200.
Yeah, here, you see, we're picking it up here. The uptake that we see in other reconstructions, we're picking it up using the robust one. I had complained about that before. And then the the Little Ice Age, we're picking it up. And it's more dynamic out of sample, which I think is really important. But also the uncertainty bands have narrowed. Yes, sir.
You are using proxies, and have you considered, or anyone has considered using historical data, histories, travel books?
Yeah, the Spanish galleons.
Well, I think that certainly is. Yeah. So.
No, it has been. There's a huge literature.
Would that be any help?
Yes, indeed it is, because it's usually oral tradition that has and writings, right, which allow us to know that there were these periods of extreme warmth or cooling, and therefore we are corroborating that using statistical or mathematical methods. So certainly those have been used.
And proxies.
Yes, but whether the qualitative answers can be converted to quantitative proxies remains a challenge. If one says it was...
There are also problems with the fact that somebody, for instance, tried to use the timing of the grape harvest or the quality of the Bordeaux wines, found that the Bordeaux wines were leading temperature. And so,
Yeah.
if you don't believe these proxies, which some people don't, the historical ones are just 1 degree worse.
I was thinking about it as a complement.
Yes. So of course they are right as a complement. They are not quantitative; they are qualitative, and they use as a complement in the following way. For example, they use as corroborating evidence for one, and secondly, as I mentioned, once if you have let's say 13 different accounts of whether it was cooler or warmer, how to incorporate them or translate them into qualitative proxies, it's quite difficult. A Bayesian approach, where one incorporates this into a prior, is possible, and we've explored that. It remains a challenge, I have to say.
Yeah, you didn't hear Graciela's talk yesterday. You might use fuzzy logic.
So anyway, so these are so here are some of the very fuzzy logic. I'm not sure whether that's a good thing or a bad thing, but.
Can you show again the result alone without that?
You see, I knew she was going to preempt me to superimpose it. It was not satisfactory, so I had this also ready.
Do you think that, sorry, I have a basic question. Do you have also the real measurements used in this, or just the proxies?
You mean the proxy records?
For up to the year 2000.
Yes.
Are you using the real observations as well?
Yes, it's in the calibration, the real temp.
How come this uncertainty should be much smaller? You have gazillions of real data. How come you have?
So essentially what we're doing is we have northern hemispheric temperature for the year 1998, for example, okay? And that's an integrated average of a space over the northern hemisphere. So we have one time series and one point in 1998, and we have a bunch of proxies, right? 79 proxies, which we are using to do a regression. So this should tell you that even during the calibration period, the predictive power of the proxies is limited.
Yeah, but
so therefore the uncertainty quantification around the regression, unless the proxies are super good predictors, we won't get the variance of y given x being reduced. Yeah.
But the real observations are there, and you have a lot, and the uncertainty, if they are included, should be much smaller in the period where we measure.
Yeah.
The thing is, they didn't use it intentionally. They only use stuff which is available 1,000 years back. So this is why uncertainty in 2000 are as bad as 1,000 years back.
Yeah, because we want to compare them. The methodology, what happens is that as Michael and Elias was saying, we just want to see that, look at the methodology and focus on the methodology and keep the proxies the same throughout and not deal with missing values yet. But we will. We will, because we do want to use the richness of the proxy information. Because there are some proxies which go back to 500 AD. I am not using it here. Because I wanted to... So
the fly specs are the
real data. The fly specs are the real data, yeah.
The real data.
You see, if look Eugenia, if you were to use the fact that each fly spec has a relatively small error bar, then the mean would lie outside that error bar. You know, it's not consistent. It's logically, I know you dislike it because it doesn't prove your political point, but it's not scientifically consistent. I mean, I'm sorry.
I mean, maybe one way to think about it is to say that when you do this regression, the uncertainty quantifier, it's a 95% confidence band around the mean, right? So unless the proxies and temperature are so perfectly correlated, we will have uncertainty that comes from the fitting procedure, from estimating the mean. So the mean could be anywhere here, because it just means that the proxies are not perfect instruments or thermometers. They have some predictive power and quite good predictive power, but they are not perfect. And that's reflected in the uncertainty.
So basically you are using just the proxies.
Yes, yes.
But
As opposed to Mike Mann, who replaced the tree rings by the temperatures.
which is
Totally illegitimate scientifically,
I
except for it would have been if he had said so in the paper.
Yes, I think, yeah, go ahead.
Each point is a temperature for the whole northern hemisphere.
Yes, from 1850 onwards. So the black point, the black dots, yeah, exactly.
The uncertainty, I mean the confidence interval for these points, how big are in comparison with the uncertainty of the moment? I mean, if you get only one point as the temperature for the whole north hemisphere, that has a standard deviation, and confidence interval also.
So I think what you're really asking is, what is the variability of the temperature compared to variable temperature given proxies?
Yeah.
Oh, it's significantly lower. Yeah, and I'm going to, so yeah, and I have the details somewhere. Of course, the proxies have some predictive power. They are good, but they are not perfect that the uncertainty is really very tight around the mean. I mean, one doesn't expect it. These are natural. I mean, there are all kinds of, as Michael pointed out, there are all kinds of errors that happen when you.
I agree completely with that, but in recent years, Mike Mann used the temperatures rightly so, because you use all the information that you have and that they...
Yeah, but you can't use temperature
But you can't call them tree rings.
Yeah, you can't use temperature to regress on temperature. That's wrong. It's like saying y equals beta times y. Hopefully beta should take the value 1.
But he called them tree rings. He should have called them observations.
Yeah, what we are doing is y is equal to beta, temperature is equal to beta times proxies. So certainly there's error in this, so we have a plus epsilon, and we're trying to get a handle on that variance of the epsilon. Whereas if you replace the proxies by temperature, you're really fitting T equals beta times T instead of P. And
that's one, yeah.
It's all of a sudden 1, and it was not 1 before.
yeah.
You know,
So that's the reason.
But the message that I naively got is that the earlier time was based on proxies and the later time on instruments.
Oh, so okay. So I think maybe where the part that may not be clear is that during the instrumental period, we do a regression between the proxies and the temperature. So we have both. Yes, we have both. So we look at the relationship. But once we have the relationship, in the historical period, we use the proxies, that model that we have fitted, T is equal to beta times P. We use that model to hindcast temperature. So that's true. We have, during this period, both. This allows us to find the relationships, the calibration. So that's true. Yeah. Okay.
Sorry for
Yeah. So does everyone understand that?
No, can I'm confused. So if I erase everything but the black curve,
Yes.
that from 1850, that's the average of the real temperatures, and to the left, that's the temperature that you got by, I don't know what kind of...
If you want to erase the black curve completely,
Erase everything but the black curve.
so you only want to keep the black curve.
Yeah.
Yeah.
Is that telling to the right of 18?
Now, in 1850, to the right of 1850, what it tells you is the temperature,
Measured by the
Proxies.
yes, measured by the proxies. If you were to use the proxies, this is what the temperature would be.
And can you put the temperature measured by the...
The actual thermometers, they're in black there. That's the,
Fly specs.
yeah, they're in those little dots. That's the actual northern hemispheric temperatures during those years. So what happens is that these little spots, do you see them? Those are the yearly annual temperatures in the northern hemisphere from 1850 onwards. That's the real data. Now, the real data is plotted there. Now, I have obviously done a regression of the temperature on proxies. The regression curve is also superimposed on this. That should show you the fact that it goes through them, that the fit is not that bad. And to the left of it, I don't have real data because we did not have thermometers. Well, okay,
Let's proceed.
let's proceed. Well, I want to make sure that everybody's on board.
Just that one thing, you're not putting it in your conclusions, it's a switching judge. Not only you have little ice age, you also have this medieval warm period.
Yes, yes.
Kind of picking up.
Yeah, so no, I do have that here,
Yeah.
actually. So uptick at the beginning of the period similar to period. So we have that little ice age, more dynamic.
Okay, so you...
Yeah, so essentially the takeaway message is that the robust reconstruction does significantly better in many aspects, including the fact that the uptick that we see here is really higher than the bands. So there's more evidence. So we've been able to reduce the uncertainty quite a bit, right? And you can see, because look at the bands here, they're the same, and then, but okay, so let me continue and say that's the main conclusion, saying that the robust approach is good. And so now I'm finally done with northern hemispheric reconstructions, right? Now, of course, I'm going to move on to now what is called spatial local reconstructions, right? And I still have half the lecture to go, so I'll try and go faster. But no, do stop me if you have questions. So I'm going to go through the first method called the Reg-EM method of Schneider, Tapio Schneider. So let's come back to this problem, right? Now, doing a spatial reconstruction, what I've done is a northern hemispheric reconstruction thus far, and I've developed it, right, from the time of Mann and Cook and Arrigo and others to when the statisticians came in to a more robust reconstructions, right? And that's the latest, one of the latest methodologies that we have. Now, however, if you want to do a reconstruction, not just for the northern hemisphere, but let's say, for the entire globe, it's a significantly more difficult task. Because we didn't have data in the first place for one time series. Can you imagine trying to do it for many time series, trying to hindcast many time series in time and space all the way back up to 1000 AD? It's more difficult, right? So how do we do it? Well, it's, and you'll see that I'll try and convince you, hopefully, that it's worthwhile trying and failing, maybe. Let's go back to the kind of data that we have. The same problem, we have temperature at different locations and proxies at different locations. Proxies go back, but temperatures don't go back except during the instrumental period, right? And let's assume for the time being that. So that means every year we have data. And from here onwards, I have data, but I don't have data in terms of temperature, but some proxies. So I assume for the time being that temperature is normally distributed with a certain mean and certain variance, mean, mu, and sigma. Okay. So every year you have a huge vector which represents the locations on the globe, and there's a temperature for each location. Let's say on a 5 by 5 grid. So it's a huge vector, and I'm going to observe it, right, of dimension 2000 about, and I'm going to observe it during the year 1990, 1989, 1987, and so forth. And of course, I'll also observe some proxies which go further back. So each of these rows represent years, and the columns represent locations, right, in space, and sometimes the proxies. Right? The question that I want, and I model it as a normal distribution initially, and that can be relaxed, and we should relax it. It can be relaxed, right? So each of these rows is a multivariate random vector, which is distributed normally, right? With mean mu, so that's the mean, the expected value, and the covariance sigma. This is an important quantity which tells you the correlation of the temperatures between location I and location j. Right? Now suddenly, because I have to model temperatures in space, I have to look at the way things are related in space. I have to do covariance modeling. It becomes quite tricky because if your random vector, if the number of points on the globe are 2,000, if you have 2,000 points on the globe, you have a mean vector, right, which is of length 2,000, and a covariance matrix, which is a 2,000 by 2,000 covariance matrix. How many entries do we have there? A gazillion? Many.
Many.
Okay, well, 2,000 choose 2, right? Plus the diagonal terms. Okay. Here, but the kind of data that we do get, this picture, this schematic representation is somewhat misleading. And what I mean by misleading is it gives the false impression that proxies go all the way back in time, right? And that's not usually true. Usually the proxies are, so sometimes they stop, there's a missing value, they go on. Here's an example. Sometimes there's missing values, and for temperature, usually we have it until 1850, and then there are missing values. But proxies, you could have missing values all over the place. So some proxies go up to here, others go all the way to the end. So there are missing values even during some proxies, for example, the corals, certain corals, well, they time sequence it, and then it goes up to, let's say, 1200 AD. And there's some proxies which go up to 1000 AD. So not all proxies go up to the time up to which you want to do a reconstruction, right? And some proxies go only up to 1600 AD. So what do we do? So we don't have, in one single row, we may not have full data even in a single row. So you have missing values in the predictors. It's a big problem, right? Part and the missing part. And I'm going to try and find a way to try and do a regression, but still take all the information into account, the wealth of the information into account. Because if I lose any of this information, it's going to hurt me, because I want to do a proper reconstruction. I want to use all the proxy information to try and, because I have very limited information, so I can't just throw away every row when there's no data. If I throw it away, I will have very few data, little data left, right? So I want a way to try and do these regressions, run a regression of the temperature on the proxies in a clever way, which is still statistically and mathematically sound and has a rigorous foundation, right? So in that sense, I divide each row into a missing part and available part. Now I know that if the temperature and the proxies are normally distributed, right, this vector can be written as a distribution with mean mu, with an available part and a missing part, and an appropriate covariance matrix. So by subdividing the random vector into subcomponents, I say this is the marginal distribution of this missing part, and this is the available part. Now, this just comes from standard. I mean, this is all I'm really doing is taking the mean vector and dividing it, and taking the covariance matrix and saying this is the covariance matrix that corresponds to the available part, this corresponds to the missing part, this corresponds to the cross of covariance, right? I'm just setting up my method, and what do I do now? I want to really use the available part to impute the missing. That's what I really want to do, because what am I really interested in? Use the available data to get the missing part, the missing temperature. But the missing is not only here, the missing is also in the proxies too, it's all over. So by doing this, the first thing that one can do when you have missing data, there is a very well documented methodology for using missing data called the EM algorithm, the expectation maximization algorithm, I'm sure which many of you have heard. And it goes as follows, right?
What does EM stand for?
Expectation maximization is one of the, I suppose, the most celebrated algorithms of the last century. We're in a new century now, I suppose. I forget. So, yeah, the EM algorithm, right? Just like your.
In case you can Google it.
Yes.
It's sufficiently well known.
Yeah, you can sufficiently well known the expectation maximization algorithm, right? So what it really does is the following, right? So when you have missing values, instead of throwing out all this data, because it's such an important question, right? What one can do is, one can start with, what am I really trying to do here? I'm trying to estimate the parameters mu and sigma, but I have missing values of this field, right? The mean and the covariance matrix corresponding to these random vectors, right? Now, if we did not have missing values, we know how to work out the mean vector. We just average those vectors to get the sample mean vector, right? And work out the sample covariance matrix. It's as simple as that. So if you have a bunch of vectors from a normal distribution, and I ask you to estimate the mean and the covariance matrix, what you would do is just average the mean vectors to get an estimate of the population mean, right? And also work out the sample covariance matrix, which really, what it really contains is the sample correlations between the ith and the jth component in the ith and jth element, right? So that's what you would normally do, but we cannot do that because of missing values. So because of that, what Dempster, Lade, and Rubin suggested was the following. They said, well, let's start with a preliminary estimator of the mean and the covariance, mu and sigma. Then I impute the missing value using a regression, because I have the available part, I want the missing value. Now what do? There is a linear regression that you can do imputing the missing, the available, right, using the available, and you can get the missing, because you can just do a regression between them. And that is given by this equation. And the regression coefficients comes from estimating elements of the covariance matrix. So what am I really doing? I'm going back here. Whenever there is a missing, I'm actually putting values in there by using this regression relationship. It's really a multiple linear regression. I have missing and I have available, right? I want to use the available to impute the missing. This is how they are related, because there are different components of a normal distribution, and when you have two different components, all you're really doing is a conditional mean. Expected value of x given y. If you know y and you want to get x, you're just replacing it with the expected value of x given y, where x and y are subcomponents of a multivariate normal random vector. That's all really that you're doing. It's just basic standard multivariate normal theory. The conditional mean. That's all this is.
You might just mention to anybody who wants to do this that you never compute numerically, you never compute the inverse of the matrix.
Yeah, so he says that if
you
you
write the sigma AA.
Yeah, so if anyone wants to do this, he said this, you never compute the inverse of the covariance of this matrix numerically. Well, I'm going to come to that in a minute.
You are.
Absolutely, I'm going to come to that, right? So once I've imputed them, right, what have I really done? Each of the places where there was a missing value, I have replaced it with the real values, because I have imputed them by using a regression. I take the available data and I use my multiple linear regression to impute them. Now I have a complete data set. But once I have a complete data set, what I have is data for every row. So I'm in a position to work out the mean and sigma just as if I had complete data, which is obvious. I just take each of the vectors for n years and average it. Here is the sample mean, and here's the sample covariance. It's nothing other than the outer product.
So the reconstruction is done at the given time?
Exactly. The imputation is done at a given time, or the reconstruction. But remember, the problem with this is that I have just started off with a value, then I have reconstructed it, infilled that entire row, and then I've got an updated estimate of mu and sigma. So I have an updated estimate of the parameters. So then now I repeat it, because mu and sigma now I can start, instead of the initial estimate, I have updated estimates, and then I use those estimates now in these coefficients. Because remember, these beta, these mu m and mu a, come from these updated estimates. So this is what the expectation maximization algorithm is. You first use the model to impute the missing values, then work out, then you have a complete data set. Well, when you have a complete data set, everything is good. Then you work out the parameters as you would normally when you don't have missing data set, and then you have an updated value of the estimator, and then you go through the process again. And you repeat, right, until I say convergence. It can be established formally that this algorithm will converge under very general conditions, right? And that's one of the big, using some, it's not very difficult using Kullback-Leibler distances. right? So, and if you're interested, I'll be happy to discuss it with you, right? So what am I really doing? Here's a schematic.
So the proof is not in the original paper.
The proof is wrong in the paper. They use a triangle inequality in the other direction. And then Joseph Wu fixed it in another Annals of Statistics paper. It's in the mathematical statistics literature. Yes, sir.
I didn't understand when you say that you repeat the steps that you already. What do you do with the data that you reconstructed?
I'm using I have complete data now. I've reconstructed. So what do I have here? These missing values that you see here, or here, they're no longer missing values. So I have a complete data set. I have rows of data. So I have vectors which come from this distribution. And I want to estimate mu and sigma. And the most basic maximum likelihood estimator is just to take the mean of those sample vectors and, of course, the covariance matrix. Once you don't have missing values, it's pretty straightforward, right? It's just the outer product of this matrix. And what it has inside is the inner product of the ith and the jth components, that's all. It's just a sample covariance matrix. The ijth element is the covariance, the correlation between the ith and the jth location is there. Yes, go ahead.
The E step is step number 1, but that's not exactly the E step, because if you just use the conditional mean, then it's what you say. But the E step is you have to condition on sufficient statistics in the top, and you have.
In this case, we have a natural exponential family. So the sufficient statistics is exactly the mean, right? So we are able to do that. That's the reason. I've actually skipped that step. So we have a log likelihood, right? And you have to condition on the available data, right? And in this case, it happens to be this mean exact. So I didn't show you the derivations, but I actually have them right here. I'd be happy to show it to you in a more complicated setting. Yeah.
Yeah, there is one thing. It's very nice explanation and everything, but there is one thing that I don't understand. If you confine yourself at reconstructing the complete
each row, yeah,
time,
yeah.
Yeah, you are missing the information that you have from the full data, even if it has many things.
No, we are not, because this sigma and mu are being updated each time. So that's from the full data.
It uses the whole.
Oh yeah, absolutely.
Okay.
You can go through each row and update mu and sigma, or as you're going through each row, you can constantly update mu and sigma, or you can do it after one full loop. It depends on your computing resources.
So, for example, if there are two proxies that are very correlated in time, that information
It's going to be used, yes.
is used.
Yeah. So it's okay. And as I said, there is more details to this because we're in a Gaussian setting. It's a natural exponential family, so there is a lot of the steps here in the expectation step, right, has been simplified. Right. The next question that I wanted to say was, here is a schematic. I'm really trying to do this relationship, right? And even among the proxies, the data is fragmented, right? And this is where I get the different inputs from. The missing values are mainly here and some here. The available values are here and here. And I'm doing these regressions. Really, what I'm really doing is I'm working out the missing values based on the available values, which is nothing more than a conditional mean here, right? Okay. Now here is a schematic of the EM algorithm, right? Essentially, I take an initial value of mu sigma, I work out the regression coefficients, which are a function, which are required for the imputation, which are taken from sigma. I do the imputation, I recalculate mu and sigma based on the complete data set, and I start again. It goes back and forth. The expectation maximization algorithm. And you can show that it converges mathematically, right? Right. And it has a variety of strengths, including the fact that it's well understood, easy to implement, relatively cheap to run, somebody else would challenge me that they wouldn't say it's fast, and I would tend to agree with that compared to contemporary methods in the convex optimization literature. Surely that's true. But the one that I have proposed relies on the normality assumptions, and we also assume that observations are independent in time, so there's no temporal modeling. I am modeling space, though, as you can clearly see. I'm not modeling time, right? And assumes missing values are missing at random. Well, we assume that missing values are missing at random. That's a big assumption, because the part that's missing happens to be during the period which we say is pre-warming, which the academic community says is pre-warming, right? So you couldn't say that this is missing at random. We assume that each of these rows are independently and identically distributed from the same distribution. And that may not necessarily be a completely realistic assumption, right? We also assume that the relationship between the proxies and the temperatures remain constant over time. So there are a bunch of assumptions that are made, and we can relax them once we understand the basic model better, right? Obviously, this method was proposed. The EML algorithm was first appeared in the statistics literature by Dempsey and Rubin, and earlier in the physics literature, and or aspects of it in the physics literature. And then it's not us who proposed using it for paleoclimate. It was Schneider who proposed it in 2001, right? So let me go and see, right? Most of the modeling hypotheses above are violated in practice. Now, one big problem is it can be numerically unstable when the sample size is smaller than the number of observations. Now, why is that the case? Because if you remember, I am working out a sample covariance matrix here. Now, this, if you have a 2000 by 2000 dimensional spatial field, right, and you have only 150 years of data, it's highly rank deficient. So I need to take a component and invert it. That's okay. That's right. It's not doable. How many minutes do we have? 5, 10?
There are lots of questions.
Yeah, there's lots of questions. This is the thing. So how does one deal with that numerical instability? It's a problem because we are faced with this high dimensional problem. As soon as I want to try and model the spatial aspect, I need a covariance model to see how points in space are related. And as soon as I have a covariance matrix to model, this quantity needs to be positive definite, right? The covariance matrix has to be positive. And the sample estimate, the sample covariance matrix, it's not positive definite, it's positive semi-definite. So certainly, it has, 850 zero eigenvalues at this point, roughly speaking. If you have 1,000 by 1,000 matrix, I think we have about 150 years of data. So it's a big problem. So
I also want to point out that you're not really answering Eugenia's question, because it says, that the assumes weaknesses, assumes observations are independent over time. No time modeling.
Yeah, what I mean is each of these rows are independent, yeah.
But there could be correlations.
Absolutely, between the proxies and of course correlations between different points. This is similar to the hockey stick methodology where we did not have time series temporal autocorrelation. Here we have modeling it in space, but we are not modeling the fact that the temperature could be related to its previous year, but more we're modeling the relationship between the temperature and the proxies and locations, right? It can be relaxed, of course. So I'm going through that process now of doing spatial, because spatial is much more difficult to do.
We actually did that, and we had a little argument with Dr. Schneider, and I told him, why don't we talk about this? And he refused to talk about it, and he wanted to go to press. And so, as usual, there was a lot of heat and no light out of this process.
Yes. Well, if it's any consolation, I'd be happy to talk to you.
No, I don't need any consolation. It just sort of it wasted everybody's time. Right?
Oh, at that time, yeah.
Is it Steve?
No, it's Tapioshi.
So
It's not Stephen. It's not Ed.
No, it's not. Yeah, no, it's not. So now, how do we deal with this? Because we have an ill-conditioned rank deficient problem. So we have a convergence issues with the EM algorithm and can give inaccurate results. So how does one deal with it? Well, the EM algorithm needs to be regularized to be applicable to paleoclimate reconstructions. Means that you have a high dimensional problem, I need to regularize it somehow. So what different people have done, okay, is that Tapio noted that essentially I'm doing a multiple linear regressions between the available and the missing. And we don't have enough of data, right? I'll go up to about 410. Okay. And there are various ways to do this regularization. One of them is to use ridge regression. It's a multiple linear ridge regression means that you take the X transpose X matrix, add plus a multiple of the identity so that it is positive, definite, and invertible. A very basic Tikhonov regularization approach. Or some kind of principal components regression. Or truncated total least squares. I'll explain what these are, right? And it's essentially a way to avoid the fact that you have an ill-posed problem. How can I still get a solution, right? Those of you who are familiar with this, I'll go through it very quickly so I can go to the final answer, which is that I'm trying to solve, the least square solution tries to solve this problem. Let's say I have solved AX is equal to B with A being rank deficient, right? The least square solution tries to get this, AX minus B, the L2 norm. What value of X will minimize this norm, right? Ridge regression, on the other hand, right, looks at the same norm but restricts the solutions to an L2 ball, right, around the origin. Right, that's what a ridge regression is, right? So what it really does is that if we don't have a solution in the least square setting when you do a regression and you don't have an X transpose X matrix which is invertible, this, right, ridge regression is a regularization approach which gives you further constraints on the problem to obtain a unique solution with good properties. And it's a staple in statistics and in applied math. There are other regularized solutions of the linear system, right? So we have this matrix A which is rank deficient. What one can do is to do a singular value decomposition of this matrix A. Just do a basic singular value decomposition. I know the applied math community loves this decomposition, so does the statistics community, right? And the least square solutions can then be written as a function of the singular values, right? In the following way, right? And instead of taking all the R singular values, you can truncate the number of singular values to K. So this is a way of regularizing the problem instead of using all the different, right, components. That's what principal components does, principal component regression. It's not very different from that. Now in the same spirit, right, ridge regression and total least squares, you do a similar problem. They're looking at this kind of optimizations where you truncate the number of components that are being used. So what I'm really trying to say is that when you have an ill-posed problem, you can either use ridge regression, right, or some kind of singular value, truncated singular value, right, approach, or a truncated total least squares approach. They're basically variants of this problem subject to some kind of singular value decomposition and using only a few of the singular values. That's all. Right? Think of it as some kind of principal component if you're not familiar with this. Okay? So this generalization provides a unique solution to a problem with multiple solutions. It has good properties, and the recent work, not only by Schneider and others, have used TTLS as the gold standard, truncated total least squares, as the gold standards, based on singular value decomposition. If you do too much of regularization, you'll get a poor reconstruction. If you don't do enough, because there's instability in the inversion process, in getting a solution, it's not good. So how much of regularization we do becomes the issue, right? So now I'm going to move on to the final part of the talk, which is now 2 or 3 slides, where I'm going to show how useful this approach is, and it turns out to be useful in practical application. Now to demonstrate that, we have a test bed. Instead of doing a reconstruction on a real paleo data set, which we can also do, we can do it on what we call pseudo proxy experiments. Now this is where pseudo-proxy experiments are, as compared to paleo experiments, real paleo proxy records, we do not know what the temperature was before 1850, right? We only know the truth after 1850. One way to see if a proposed method in the literature does very well, there's been an established methodology that has come up in recent years, and I'll take you through that. So what one usually does is one takes GCM output, so general circulation model outputs or climate model outputs, all the way during the instrumental period and even before. So we have some kind of ground truth. It's just a basic test bed, right? And then what one does usually is take these spatial fields, add noise to them, right? And then try and see if one's proposed method can reconstruct the truth during the instrumental period and even during the historical period. But in this case, the truth is known, so we can compare it to the truth because we have GCM output, right? Global climate model output all the way back. This is an established methodology that's been used by many, and it's called pseudo-proxy experiments. It's thought to be reflective of the geophysical aspects of a spatial field because the GCM output has spatial structure, observes the spatial structure in the climate field, or it is expected to, right? So here, the advantages that we have some kind of ground truth, and what one happens is that one takes the locations where there are proxies. For example, here they are in the real world, but takes those points in the GCM output which correspond to real proxy locations, corrupted with noise, so you have some kind of realizations which you could call pseudo proxies, and then we try and reconstruct the entire global field based on these pseudo proxies. So it's sort of like a simulated environment in which one does these experiments. And then you can measure. So every year you can reconstruct spatially the climate field. And you can say, well, how do I work out the pseudo-proxy? I call TST, the simulated temperature from a GCM model. I take it and I corrupt it with Gaussian noise. And then I make T hat ST a reconstruction of my climate field, TST. Of course, and then I can work out performance metrics, which is things like the mean squared error, the truth minus what I reconstructed, like in L2 norm, across the entire field. And then I can also compare an approach that I have, like RegEM, to just using the mean. Instead of using a regression based on a relationship between the proxies and the temperature, I could just use the mean, standard mean, which is a very basic quantity to use. So can I do better than just using the mean as compared to borrowing strengths from the relationship between the proxies and the temperatures? And that can be measured by something called the coefficient of efficiency. The closer it is to 1, the better. The negative, when it's negative, it's not very good. So what this methodology allows us to do, as I said, is to really establish if a proposed method, a reconstruction method, is useful when we know what the truth is, in some sense, right? When we do that with the TTLS, and here are the last 2 or 3 slides where I actually take you through them. Here was the global mean reconstruction from 2000 to 800 AD. Black lines are the target based on a GCM output. This comes from the National Center for Atmospheric Research GCM model, right? Output from that. The red is the TTLS. As you can see, TTLS is really able to get it quite well, globally, right? This is an entire global mean reconstruction. I'm interested in local reconstructions, the entire spatial field as compared. So globally it's doing quite well. But when I look at it spatially, here's the globe. When it is white or red, that means the reconstruction is better than using the mean. When it's blue, means that it's worse than just using the standard mean in the historical period, in the verification period. Clearly you can see it only does well locally in North America and in Europe. It doesn't do very well, as you can see. It's better to use the mean. So spatially the method is not very good. Right? And that is a problem. And we were wondering, well, we couldn't really understand why was it doing so well globally. It seemed to really get the black dot, the target, very well from that the GCMs evolution very well, the method, TTLS, right? But it's not able to get the spatial one correctly. So what we did then was we looked at each of the locations where there was a positive bias and a negative bias, and we plotted them. And what we found out, the red lines are the positive bias, and the blue lines are the negative bias from TTLS, and the black line is the average. What we found out was that when you do a spatial reconstruction, the positive bias and the negative biases were cancelling out. So in fact, even though it seemed very good globally, it was coming out from cancellations, upwards and downward biased local reconstruction. So the spatial reconstructions are not particularly that good. So one shouldn't be misled into thinking just because one gets a very good global reconstruction from truncated total least squares, it doesn't necessarily. So it's, as I said, it's an extremely challenging problem. Then we also try to do it for North America and Europe, just only locally. And there, in parts of the, there are some positive improvements as compared to using the mean, but over the Great Lakes region, it's pretty poor. And also in continental Europe, it's not so bad, but over Russia and the Caucasus, not very good. So meaning that the methodology, when you try and do it over space, spatial reconstructions, there are various challenges that we have. And tomorrow I will propose another method which tries to overcome this even spatially. Just like we had proposed a method to overcome the hemispheric temperature approach using a robust approach. Let's see if we can overcome the problem here. What is the main problem here? The main problem is that...
Sorry, is the coefficient of efficiency in this case actually negative? In other words, the variance of the reconstruction is large?
Yes.
Yeah.
So
okay,
it's...
so you are actually... It looks like it's not very regular.
Yeah.
It pushes things.
The method is not very good spatially. This is the problem. And one could be misled into thinking that because of this picture globally, that it's good. But if your intention is to do it locally, there are issues with this. It's obviously one of the gold standards in the method, and all credit to the author, because the method it has been used by so many people and is a major step in the methodology. However, there are some improvements that can potentially be made. What I think the main problem, at least the way I see it, is that it's a very high dimensional problem. And it's not so clear whether the kind of regularization that we are using achieves the kind of dimensionality reduction that is appropriate or required to do it. And tomorrow I will propose a method which tries to achieve that dimensionality reduction, and to still do a spatial reconstruction, right? Which, as you can clearly see, is much more challenging. So I think I'll stop here with acknowledgements. Okay.